today we'll study about Nyquist plot. So we'll first learn how to draw them. Following this we will be discussing the concept that goes in plotting Nyquist plot, because that way it is easy to understand. Drawing Nyquist plot is comparatively easy as opposed to the underlying concept, of course, if you know how to draw polar plots. So to draw polar plots, you'll have to refer to my previous video on polar plots, and I suggest that before you watch this lecture, it's better if you go through that lecture where I have explained how to draw polar plots, because without the understanding of polar plots, you will not be able to draw Nyquist plots. Well, there are a few points associated with Nyquist plot. The first is that it gives information on absolute stability. The absolute stability, as well as using Nyquist plot you can know the relative stability of two stable systems, and moreover you can find the degree of instability. Of course, unstable systems. So these are the three information that you can attain using Nyquist plots. One is that if you're given a system, you can through the Nyquist plot know whether that system is stable or not. So which is taken into account the absolute stability of the system. The second is if you're given two systems which are absolutely stable. So if you're given two stable systems, then you talk about which of them is more stable. So here's where there comes the concept of relative stability. And the third is if you're given an unstable system, then you can find the degree of instability that system has. Or in other words, you can talk about two unstable systems and find which of them is more unstable compared to the other. Now in Nyquist plot, what you do is you consider the function GSHS is considered instead of the closed loop characteristic equation 1 plus GSHS. So whenever you plot Nyquist, while plotting Nyquist plot, the function that you will have to consider is GSHS and not 1 plus GSHS. So while plotting Nyquist plot, the function GSHS is considered instead of the closed loop characteristic polynomial 1 plus GSHS. So what is closed loop characteristic equation? So this is something that you must have studied in previous units. So you can, just for remembering, you can write this as, so this characteristic equation comes from the transfer function of the form g over 1 plus gh. So if you equate the denominator polynomial 1 plus gh equal to 0, so this particular polynomial is termed as characteristic equation. Once you draw the Nyquist plot, the stability of a closed loop system as well as that of open loop system can be determined. So this is one more benefit of Nyquist plot, that if you draw Nyquist plot, so from Nyquist plot, stability of closed loop system as well as open loop system can be determined. Now we will talk about the procedure that is involved in drawing Nyquist plot. So I again repeat that you go through polar plot before going to through the procedure of drawing the Nyquist plot. So you'll have to first, in the first step, draw the polar plot of GSHS. So note that we are going to draw the polar plot of GSHS and not of 1 plus GSHS in order to draw Nyquist plot of any system. And of course this will be drawn for omega lying between 0 and infinity. So that is, you're talking about the range of omega between 0 and infinity. There's one correction in the previous lecture, and this correction I'll show is when I found the intercept with the real axis, so I came up with the values of omega, two values of omega plus minus under root 2. So this has to be corrected. So the value of omega should be taken as plus root 2, because we are talking about the range lying of omega lying between 0 and infinity, which means that we'll be having positive values of omega, and thus minus root 2 would be discarded, and we'll be talking about only root 2, which will be lying between 0 to infinity. So after drawing polar plot for the range of omega lying between 0 to infinity, the next is to draw to extend the plot for the values of omega lying between 0 and minus infinity. So the next step says that draw the plot for omega, we'll be drawing it between 0 and minus infinity. So let's call the 0 that lies towards negative axis as minus 0. So we are assigning a minus sign. Just remember that we are going to talk about the negative values of omega to omega equal to minus infinity. So this is done by simply taking the mirror image. So you will be taking mirror image about the real axis of polar plot. So the second step is quite simple. So if you're going to talk of taking mirror image about real axis, so if suppose this is the graph and you have a real axis which is the horizontal axis or the x-axis, so the polar plot which would be drawn using the procedure which had been discussed in the previous lecture. So after obtaining the polar plot, you'll be simply taking the mirror image about the horizontal axis, about the real axis. So that mirror image of the plot will be nothing but the plot corresponding to omega lying between 0 and minus infinity. For example, if we talk about the previous problem we did in polar plot, so the plot that we obtained there was something like this. It was something like this, and this was the real axis while this was imaginary axis. So we sometimes refer this axis as sigma and this as j omega. So in order to plot the second step says to plot for omega lying between 0 and minus infinity. This can be achieved by taking the mirror image of the plot of the polar plot about the real axis. So this is real axis, and we're going to take the mirror image of this plot in this manner. So this would be the mirror image would look something like this. So this is what the second step says. Now follows the third step, which says that we'll have to join the point corresponding to 0 for positive side of omega and 0 at the negative ranges of omega. So let's write this. So join points corresponding to omega equal to minus 0 and omega equal to plus 0. So again, these are 0 cannot be given any sign like minus or plus, but we are writing minus and plus just to identify zeros which lie on the negative and positive side of range of omega respectively, and you'll have to join these points in clockwise direction. So this will be, if you join the points omega equal to minus 0 and omega equal to plus 0. So what are these points on the graph? So if you remember in the previous graph that we draw for polar plots, the point omega equal to 0 plus 0 was this. So this was actually plus 0, and the point, this was omega infinity. So we drew from point 0 to infinity in this manner, and now we are taking the mirror image of this plot, and this point will correspond to omega minus infinity, while this point will correspond to omega equal to minus 0. The third step says that to join the points corresponding to omega minus 0 and omega plus 0 in clockwise direction, which means that you will have to join the points which of course will be having a radius of infinite. So the radius of this arc will be infinite, because the points plus 0 corresponding to omega equal to plus 0 and omega equal to minus 0 are somewhere at infinity. Thus if you join these 2 points, then the arc that you get will be having a radius of infinite, and this will be done in clockwise direction. So this is how the the Nyquist plot or the polar plot flows. You drew the polar plot starting from omega 0, and this was drawn in the clockwise direction, which attained omega equal to plus infinity. And again, after taking the mirror image, you'll always talk about this graph to be moving clockwise, and then again completing the circle, touching the points minus 0 and joining the points minus 0 and plus 0. So since I told you that the radius of this arc is infinite, so let's write this. So this will be enclosing the right hand side of the this in fact was S plane, so we'll be referring this as S plane, and this will be having an infinite radius. And now at what angle these 2 points omega equal to -0 and omega equal to +0 will be enclosing. So we'll be giving a table about the angle that this arc will be forming between the points -0 to +0. So if you look at this particular figure, you will find that the angle that this arc covers is about -180 degrees. So this is -5 degrees. So depending upon the type of the system, you have different closing angles. So we'll draw that table. I don't have much space left, so let's try to inculcate that table in this place. So if we talk about the type of the system, so if type of, and since we are talking about system, or we are constructing the polar plot or Nyquist plot for GSHS, so closing angle, so this is the angle that will be closing between the points omega -0 and omega +0, and of course the radius of this arc that encloses, that joins the 2 points -0 and +0, omega -0 and +0. So if you are talking about a type of system, that is 0. Okay, one more thing, the type of a system is decided by the term of type S. So in the denominator polynomial of the transfer function g/1 plus gh, so this one. So this was something that was again missed in the previous lecture. So if you have a term s to the power n, so the type of the system is decided by the value of n, and if this value of n is 0, then type is 0. If this value of n is 1, then the type of system is 1, and so on. Coming back to our subject, so if the system is a type 0 system, and moreover notice that we are talking about type of GSHS and not type of 1 plus GSHS, or not the type of the transfer function g/1 plus gh. So this is the type of GSHS. So after writing the function corresponding to GSHS, for example, let's say GSHS came out to be equal to s/s. So if GSHS came out to be equal to 1/s into s plus 1, so we are talking about this function. So we have a term s to the power 1, so the type of the system is 1. Had this power be 2, this system would have been a type 2 system. If this power was 0, which means that this term was absent, so this is a type 0 system. So for a type 0 system, the closing angle between omega equal to -0 and omega equal to +0 will be 0, because the 2 points will be coincident. For a type 1 system, the closing angle will be -pi, and the radius of the arc will be infinite. So now since you're talking about an arc that will exist between the 2 points -0 and +0, thus that arc would be having a radius of infinity. If you have a type 2 system, in that case you will be having the closing angle of -2 pi. So that will almost be covering the entire S-plane. And again, for a type 3 system, this would be minus 3 pi infinity and so on. So type 4 you'll be having minus 4 pi, for type 5 you'll be having minus 5 pi. And in general we can say that if you have a type n system, then the enclosing angle will be minus n pi of infinite radius. So with this basic idea, let us try to do a problem, and we'll construct the Nyquist plot of the same. So for the example that I took before for constructing the polar plot, I leave that example on you to construct the Nyquist plot yourself. I'll be doing another example today. So there is a shorthand method of constructing polar plots. So just to know how the polar plots are, what type of polar plot the function will be having, so that shorthand method will be discussed later on. But if you're going to use that shorthand method, you won't be knowing the intercepts and the points, the magnitude of the values where that will be meeting the real or imaginary axis. So let us do our first problem on Nyquist plot. Let's say we're given the function gs hs as 100 over s plus 1 s plus 2 s plus 1 s plus 2 and s plus 5. So this is the function gs hs, and we're required to draw the Nyquist plot of this function. And it is clear that this function is a type 0 system because we don't have any term of the type in the denominator s to the power n. So n here is 0. And so we start first of all applying the rule. The first step says to draw the polar plot. So going back to the previous lecture, if you remember the steps that are involved, which are as follows. So these steps will be applied again on this particular problem in order to obtain the polar plot of this function. So let us first draw the polar plot of this function. So in order to draw the polar plot, step number 1 says to ensure that this function is given in time constant form. So ensure that this is given in time constant form, which means you simply have to take out the constant which are inside the brackets added with s. So we can write this as 2 into 5 1 plus s 1 plus 0.5 s and multiplied by 1 plus 0.2 s. So this is time constant form. The second step says, so we call this first, the second step says to put the value to substitute s equal to j omega in order to obtain the frequency function. So you substitute s equal to j omega, and thus you will be getting j omega h j omega, which will be equal to 100. So we further simplify this. So this is 25 into 10, and you get in the numerator as 10 divided by 1 plus j omega 1 plus 0.5 j omega and 1 plus 0.2 j omega. So you got this frequency function. And third step says to separate them into magnitude n. So you will be separating them into magnitude n phase. So you will be obtaining the magnitude gh, that in short refer to this as gh. So instead of writing j omega or s again and again, so I'll be referring this as gh. So let's say gh, the magnitude of gh can be written as 10 over under root 1 plus omega square 1 plus 0.5 omega square and 1 plus 0.2 omega square. So this is the magnitude of the given function. And the second is to obtain the phase angle. So the phase angle of gh can be written as, so again the same procedure you can assume in the numerator as 10 plus j 0, so that will correspond to 0 angle, and all the other terms in the denominator will contribute negative phase. So the first term gives you minus tan inverse omega upon 1. The second contributes minus tan inverse 0.5 omega, and the third contributes minus tan inverse 0.2 omega. So the fourth step in drawing the polar plot is to put the limits. So you will be obtaining limit for omega 0, the value of magnitude gh. So if you put 0 here, you get these as 10, and for limit omega tending to 0, the angle gh, if you put 0 there, you get this as 0. And again the fifth step says to obtain limit omega tending to infinity magnitude. So if you put omega infinity over here, you get this value as 0, while limit omega tending to infinity angle gh comes out to be equal to, and so if you put omega infinity here, you get this as minus pi by 2. This also gives you minus pi by 2, and this minus pi by 2. So you get the angle as minus 3 pi by 2. So from step 4 and 5, what you get is, what you did is you obtain the two extreme points of the curve of the polar plot. So let us first draw this on the graph paper. So suppose this is the imaginary axis, and let's say this is the real axis. So for omega equal to 0, we have the value, the magnitude as 10, so that would be lying 1 2 3 4 5 6 7 8 9 10, and the angle is 0. So this is the point where you have the value corresponding to omega equal to 0. Similarly, the second point, which corresponds to omega infinity, is having magnitude 0 and angle is minus 3 pi by 2. So magnitude 0 means that the point will be lying at the origin of this plane. So if this is the S plane. This is the g omega axis or the imaginary axis, while this is the real axis or sigma axis. This point corresponds to omega equal to infinity. And as I told you previously, that the magnitude is 0, the angle is minus 3 pi by 2, and the information this angle gives us the curve that will be approaching omega equal to at this point will be through the minus 3 pi by 2 line axis. So if this is minus pi by 2, this is minus pi, this will be minus 3 pi by 2. So the point will be approached through the minus 3 by 2 axis. And since the polar plot moves clockwise, so you will be having, once you start increasing omega equal from omega 0, you start increasing omega values of omega, the curve will be moving in this manner. So things will be moving clockwise. We can infer from this plot is that we are going to have two intercepts, one on the vertical axis somewhere at this point, and the other on the real axis on the negative side somewhere at this point. So because the polar plot will be drawn from this point in the clockwise direction, and then thus we'll be having two intercepts on imaginary as well as real axis. So I leave this to you to find the values of omega and intercepts at real and imaginary axis. I simply write the broad step that was used to obtain the real and imaginary axes. So in order to obtain the intercept, you first have to take out the real and imaginary part from the magnitude GH, from GH, not the magnitude. So you'll have to get this function GH broken down into real part of GH plus the imaginary part of GH. So this can be done by multiplying with the complex conjugate of the terms which exist in the denominator of GH in complex form. For example, you have terms like 1 plus j omega. So you'll be multiplying and dividing a term 1 minus j omega. So you'll be having a term 1 minus j omega in the numerator as well as denominator. Likewise, you have another term in complex form 1 plus 0.5 j omega. So you'll be multiplying and dividing in the numerator and denominator by its conjugate, which is 1 minus 0.5 j omega, and similarly you'll be multiplying and dividing the numerator and denominator and the expression, this term by this whole function by 1 minus 0.2 j omega, and thus you will be obtaining a real from that and an imaginary part separate out. And so I got the intercepts as on the imaginary axis. I got the intercept, so when the real part is 0, I got this magnitude as minus 5.6, and when imaginary part is 0, the magnitude comes out to be minus 0.75 approximately. So I leave the subsequent steps after this on you. So taking these two points on the S plane, so the 2 points are at, one of them is at minus 5.6, which is 1, 2, 3, 4, 5, and 5.6 will be approximately at this location. So we got the first intercept of this curve. So this curve will be starting from this point and reaching this point, crossing it. Then we'll be having a second intercept, which is minus 0.75, and that point will be somewhere here. So these are the intercepts. So now in order to draw the polar plot, we simply have to join all the 4 points which we obtained in the 7 or 8 steps we studied while drawing the polar plots. So I guess this was step 8. So by applying step 8, you get the intercepts. I repeat this again, you'll have to apply step 6 completely, then there's a step 7, then after step 7 you apply step 8 in order to get the intercept. So I skipped step 6, 7 and 8 and have written directly the answer, so you can verify this on your own. So once you obtain the 4 points, the starting point and the end point and the 2 intercept, you simply will have to connect these points in this manner. So this point comes very close to origin. So you will be having your polar plot in this manner. So if you magnify this portion, it will be looking something like this. So this is the intercept point 7, 5 or 7, 6. This is the origin. Now coming back to the Nyquist plot. So again, look at the rules that we studied in Nyquist plot. The step number 1 says to draw the polar plot, which has been completed. Step 2 says to obtain the mirror image in order to plot for omega 0 minus 0. So the plot will be obtained between omega minus 0 and omega minus infinity. So to obtain the plot corresponding to these value, you'll have to take a mirror image about the real axis. So the mirror image would look something like this. So 1, 2, 3, 4, 5, 6. So this is 5.6. And we'll be connecting this. So this particular point, the last point that we obtained, corresponds to omega minus 0, while this was the starting point was plus 0. For polar plot, the last point correspond to omega plus infinity, and this point, while taking mirror image on the negative drawn downwards, the first point will correspond to omega equal to minus infinity. Now if you look at the step 3 of Nyquist plot, so it says that if you have the type of system as 0, so which is seen from here, so s to the power 0, the value of n is 0, which means you have s to the power 0 in the denominator of GSHS, which is a type 0 system. So this is a type 0 system, and hence the points corresponding to omega minus 0 and plus 0 are coincident. So they are coincident at this particular place, which means that you will not be getting any arc of infinite radius in this problem. Had this type other than 0, the type of the system other than 0, in that case you would be getting arcs of infinite radius, and depending upon what the value of that type of system is, if it is going to be 1, then the circle that would be formed will be minus 180 degree, and so on. So which means that the graph that we see here is the required Nyquist plot. So this is the Nyquist plot of the function given GSH is equal to 100 over s plus 1 into s plus 2 into s plus 5. So in the next class we'll try to understand the concept of Nyquist plot, the underlying concept, what and how the Nyquist plot is obtained. Okay, there is one correction over here, is that this is not the S-plane, rather the GSHS plane. So we will be drawing Nyquist plot on GSHS plane, which has already been discussed in step number 1 or 2. So we will be operating always in GSHS plane. Here we will be constructing the Nyquist plot using MATLAB, which will give us the exact plot. So we write the transfer function of our example as TF 100 was in the numerator, then we had s cube plus 8s square plus 17s plus 10.
So we got this after opening all the terms in the denominator, which were s plus 1 into s plus 2 into s plus 5. So when we multiply these three terms, we'll get s cube plus 8s square plus 17s plus 10. So this becomes the denominator. And then now Nyquist of the transfer function gh. So this is how the plot looks like. So this is the exact plot which we'll be getting from the given problem when we plot it on MATLAB.